Hello, ladies and gentlemen. We are going to work on lesson 14.4 and 14.5. All right, so we are going to have a quiz on Monday and Tuesday next week, May 4th and May 5th. It's going to be a 10-point quiz like we normally have, that chapter quiz. And I'll post it with a Google form to fill it all out. It's going to be for 14.1 through 14.5, what we're learning today, actually. And then because quizzes normally only take 20 to 30 minutes or so, I am going to try to put together a lab simulation, whether it's a kitchen lab that you can do in your kitchen or a lab simulation. Basically, it'll be a fun little easy 10 points for you on top of the 10 points for the quiz to put a few more grades into the grade book. All right, today we're going to learn about weak acids and weak bases. They basically are the same concepts, so that's why I'm combining both of these sections into one video. So let's go ahead and start. We are going to start with a review question. So first, what is the hydroxide concentration in a nitric acid solution that has a pH of 3.45? Now, when you are problem solving, it's best to write out what you're given, and also what you're asked for. So we're going to start by writing hydroxide. That is what we want. So in your mind, you should be thinking about all of the equations that include hydroxide. You start scanning your periodic table. Which equations include hydroxide? Well, we have 10 to the negative POH is equal to hydroxide. So if we had POH, we could solve for that. We also know that hydroxide times hydronium is equal to Kw, which means when you rearrange that, hydroxide is equal to Kw divided by hydronium. So if we can find hydronium from the rest of the information in the problem, we could use that equation to get to hydroxide. We are given, though, pH. pH has a 3.45. We also have an equation, pH plus POH equals 14. So we can use our pH of 3.45 to find H3O using our 10 to the negative pH is equal to H3O. Then you would plug in H3O into here and find your hydroxide. And that would be one way to solve it. You could totally do that. However, I think subtraction and addition equations are much easier. So if we plug in our pH of 3.45 into here, basically you're taking 14 minus your 3.45, you would get POH. Then plug in POH into this equation. So we're going to do that way just because I think it's a lot simpler doing addition and subtraction. So we have 14 minus pH equals POH. So that's 14 minus 3.45. I mean, this is so easy you could practically do it in your head. 10.55 is our POH. Let's plug that into this equation. We have 10 to the negative 10.55 is going to equal hydroxide, which is the answer to the problem. 10 to the negative 10.55. And we have 2.818. Significant figures. Our pH is given with two decimal places, so that overall your end answer needs to just have two significant figures. So we're going to do it that way, rounding it this way, times 10 to the negative 11. And that is your hydroxide concentration. That would make sense that you have a very, very tiny amount of hydroxide in an acid solution. This is nitric acid. In fact, it's a very strong acid. All right, so we have weak acids. Here you have your general acid equation of HA with water turns into A minus and your H3O. Now that's be almost the identical equation that we have for strong acids. The only difference is that in a strong acid, you have one arrow pointing to the right, and you don't have that double arrow that we have here. And that's because in a strong acid, your acid completely dissociates. It's going to completely break apart. All of the hydrogens break apart from all of the anions. You don't have any left over. So all of the reactants turned into all of the products. In a weak acid, they only partially dissociate. So not all of your hydrogen ions are going to separate from the anion, which another way to think about that means some of your products, some of the hydrogen and your anion join back together and turn back into reactants, which is why it goes back and forth. This is called your equilibrium reaction rather than a completion reaction. So when we were saying that your concentration of strong acid equals H3O concentration, that works only for strong acids. It doesn't work for a weak acid. Your weak acid concentration does not equal H3O because we don't know how much of it turns into H3O. So I'm going to write that out, our general acid equation. We have HA, where H is your hydrogen and A is representing any anion, whether it's a single element anion, like in your first couple of columns on the periodic table, or it's a polyatomic anion from your polyatomic ion list. And water. Double arrow turns into A minus, and that's because a weak acid still has a definition of an acid. It still donates or gives up or produces a hydrogen. So the hydrogen leaves the acid and joins the water. So now we have 3 hydrogens attached to our 1 oxygen. And of course we have our charges. Notice the charges are balanced as well. You've got a negative charge and a positive charge, so an overall neutral matches the overall neutral here. So yes, we still have a 1 to 1 to 1 to 1 stoichiometric coefficients, but we don't get to cross over. We don't get to say that however much of this is what we have of this. So for example, if we had 10 of these molecules, we don't automatically have 10 of these. We don't know how much of these are going to break apart. Maybe only 1 of them will. Maybe 5 of them will. We don't know. Each weak acid is actually different in that. All right, for the next part, equilibrium expression. If you guys remember, our equilibrium expression is products divided by the reactants, and you only use your aqueous compounds. You don't use solids, liquids, or gases. And this is how we got our Kw equation from water. And I'll show you the equilibrium expression for this in a moment. Well, I guess I'll do it right now. It's Ka, A meaning acid, where before we had water, so we had Kw. Here's your acid dissociation equation. These are aqueous. It's very important to include everything, all your states of matter. So we have 3 aqueous compounds and 1 liquid. We don't include the liquid. So write our products out. We have the concentration of A minus times the concentration of hydronium divided by the concentration of HA, and water is excluded. Okay, so there you have it. Products divided by reactants. If you have more than 1 product that is an aqueous compound, then you multiply them together. If you had more than 1 reactant that they were all aqueous, then you can multiply them together. In this case, we only have 1. So we have these 2 multiplied, divided by your reactant. There you have it. Here's a list of all of the different Ka values. So in essence, your Ka number is going to tell you how much in a weak acid is going to dissociate, how much of those hydrogens actually are donated from your acid, because not every molecule is going to donate its hydrogen. The higher the value of Ka, the stronger the acid. The higher the value means more of the molecules gave up their hydrogen, and that is more like a strong acid, so therefore it is a stronger acid when your Ka is higher. So in this chart, you have the names of the acids, you've got some structural formulas. You can see the little blue hydrogen in there is representing your acidic hydrogen. Not every hydrogen in a compound is going to be considered acidic or given up in an acid reaction. So only the blue ones in the structure are showing the ones that are actually the acidic hydrogens and that could be given up. So then the next column is showing you the conjugate base. So what does this compound look like after it has lost its hydrogen? It's just showing you the structure, or the formula, not the structure. Then you have the full reaction given out. Your acid plus the water turns into the conjugate base NH3O. Then you're given the value of Ka. And you can notice all of those numbers there, starting at a times 10 to the negative 4, all the way down to times 10 to the negative 2. So that is in decreasing value. As your exponent is getting smaller and smaller, which means the value is a large number, but it's negative. So it's going smaller on your number line. If you imagine a number line, times 10 to the negative 4, that first one is a larger value than the times 10 to the negative 10 at the bottom. Which would mean your top one on this list, hydrofluoric acid, is stronger acid than all of the rest underneath. They're all considered weak, though, still. All right, so let's try a practice problem. I will move this so we can see it a little better. I'm going to cover the reaction for a moment. All right, the pH of a 0.1 molarity solution of nitrous acid, HNO2, at 25 degrees Celsius is 2.17, so that's our pH. Calculate the Ka for nitrous acid at this temperature. So we have our chemical reaction. We have our acid and water, and we have our conjugate base NO2- and H3O, which means we can come up with our Ka equation quite simply. Let's go ahead and just adjust this. Our anion is NO2, nitrous acid, when it is an acid here. Therefore, we just need to change this to that. And down here, we have HNO2. So we need to find Ka. So we need to plug in all of these numbers here. We need to find H3O, we need to find NO2 minus, and we need to find HNO2. Now, it's telling us that originally we had a 0.1 molarity solution of HNO2. We can't exactly use that, though, in place of here, because that's initially or originally. We need to find the equilibrium concentrations, because as soon as some of this dissociates, we're going to have less concentration of that. We don't know how much less, so that's what we have to figure out. The other thing to note is that the stoichiometry ratios actually work for on the same side of the equation. So this is a 1-to-1 ratio. So if we can find H3O, which we know we can from pH, then we would also have the concentration of NO2. These two are going to be equal. And then over here, these are going to be equal, though the water, of course, doesn't play into the number and the math. So we have a pH of 2.17. Therefore, if we said 10 to the negative 2.17, we can find H3O. So grab your calculator and let's try that. 10 to the negative 2.17. .00676. That is equal to H3O and NO2 minus. So we've got quite a bit here so far. Now, let's keep that number in mind there. And let's also keep our Ka in mind. But we're going to write something out for a moment. We need to figure out the equilibrium concentrations for each of these. So we need to write out what's called an ICE table, ICE. You only draw it. I think I've got it on the next slide, actually. Indeed. You only draw this ICE table for your aqueous compounds. So we don't need to use water at all, just like we don't have it in our Ka equation. So I stands for initial, C stands for change, and E stands for equilibrium. Initially, so this water, we don't have water at all in the math. We can just ignore it. But for HNO2, initially, the problem told us it was 0.1 molarity. And initially, we had 0 NO2 minus and 0 H3O. We know from finding the pH of 2.17, we then calculated that our H3O was equal to, let's put that in scientific notation to make it easier, 6.8 times 10 to the 3. So there is our H3O. That is at equilibrium. When you measure pH, you're measuring the concentration of H3O. So initially, there should be no pH for this because we don't have any H3O. But as soon as it starts dissociating, it's going to completely dissociate as much as it's going to, not completely as in all of the hydrogens. So you can't really calculate pH without it having reached equilibrium and is at equilibrium. So then your H3O concentration that we calculate is on your equilibrium row here. Now, like I said, these two stoichiometrically are equivalent because they still have a 1-to-1 ratio. So we can use this. So we need to find what's the concentration of your HNO2 at equilibrium. Well, let's look at our change here. This changed from 0 to 6.8. So that means we added by 6.8 times 10 to the negative 3. So we have a little plus 6.8 times 10 to the negative 3. In order for that much to be produced, that same amount had to decrease on this side. So we have a negative 6.8 times 10 to the negative 3. So in that way, you do have stoichiometry and your coefficients here. So 0.1 minus 6.8 times 10 to the negative 3 is our equilibrium concentration for HNO2. Now we have our ICE table set up and we can put in our Ka values. If you remember our Ka equation, we're going to have NO2 minus times H3O plus divided by HNO2. So let's go ahead and write that out as well. We have Ka is equal to, we've got 6.8 times 10 to the negative 3 times 6.8 times 10 to the negative 3, which is the same thing as saying it's squared. And then our equilibrium is going to be 0.1 minus 6.8 times 10 to the negative 3. That is your equilibrium concentration of HNO2. So let's go ahead. I will make this larger so you can see it, and then let's go ahead and calculate that out. We've got a lot of parentheses we need to use here to make sure we get the right number. So I have 6.8 times 10 to the negative 3 squared. That gets me 4.624 e negative 5, e meaning times 10 to the, and there's your exponent, negative 5. And then we've got 0.1 minus 6.8 times 10 to the negative 3. And that gets us 0.0932. All right, then we can put these in. So I have 4.96 times 10 to the negative 4 as the Ka value for nitrous acid. And that is it. All right, we're going to do a lot of problems. I know these seem a little bit daunting and confusing at first. There is our ICE table all written out. And then we also have the equations for pH and finding H3O there. All right, let's go to the next one. We have our Ka equation, or the acid dissociation constant for HNO2. So, and I have written there, you must use concentrations when your solution is at equilibrium in order to find Ka. All right, here is another problem. It says niacin is one of the B vitamins that our body needs, and it has this molecular structure. So I showed you a modified version of a Lewis structure, and then your space-filling molecule. The structure is not important actually to this problem. It's just out of curiosity. That's what your one of the B vitamins look like. All right, so the problem, a 0.02 molarity solution of niacin has a pH of 3.26. What is the acid dissociation constant for niacin? First thing to remember is that acid dissociation constant means Ka, and then you have your equation here. Through logic, we can figure out which compound is the niacin, because we know it's not water, the H2O, and we know it's not H3O. So then the other compound in your reactant side must be niacin, the C6H4NO2H. That last H on the very end is the acidic H, or the acidic hydrogen. It is written separated from the rest of the hydrogens to remind you or to tell you, hey, this is your acidic hydrogen, this is the one that's going to be lost. As you can see on the product side then, you have that same compound, C6H4NO2 minus. It just doesn't have the hydrogen in there. All right, so we need to solve this problem. Let's go ahead and write this out. We need still the ice table here because we need to find the Ka of our niacin. Let's go to the next slide. I have our ice table written out here. So we have the problem is written out, and we are not going to include water in our ice table. So initially at the very beginning, what concentrations do we have? Well, niacin, it says, is 0.02 molarity. That is originally or initially before dissociation happens. So that is where we put that at the top for 0.1 for your I, or initial. I'm going to abbreviate this as C6. No, that's going to be too confusing. We're not going to abbreviate anything. We're going to ignore water for right now because it's not going to be in your ice table. And then we have on the other side C6H4NO2 minus without its acidic hydrogen. And then we have H3O. We need all of these values at equilibrium, not their initial concentrations, but at equilibrium in order to plug them into our Ka value. Because our Ka for this is going to be your conjugate base, C6H4NO2 minus times H3O, divided by your acid, C6H4NO2H. Oops. Let's just make this bigger so you can see it. Okay. So we have initially 0.1. Is it 0.1? No, it's not. It is 0.02. Initially, we have 0 of these because it hasn't started dissociating yet. At the end, equilibrium, our H3O can be found by using the pH. So if we say 10 to the negative pH that's given in the problem, 10 to the negative 3.26, we get 5.495 times 10 to the negative 4. These are stoichiometrically equivalent, so this also, at equilibrium, has the same value. 5.495 times 10 to the negative 4. That means we know it changed by this much because it started out as 0. It changed, or it added 5.495 times 10 to the negative 4, which then means your change row needs to all be the same value. On the reactant side, they're decreasing by this much. 5.495 times 10 to the negative 4. And we are increasing by that much on the product side. That is then how we can find our equilibrium concentration. We're going to have 0.02 minus the change. Now we have all of our equilibrium values that we can plug into here. We've got 5.495 times 10 to the negative 4 for here, times the same value for H3O, so it's this value squared, divided by 0.02 minus 5.495 times 10 to the negative 4. So let's try that. 5.495 times 10 to the negative 4. We're going to square that value. So we have 3.01. Actually, it rounds to 3.02 times 10 to the negative 7. Then divided by 0.02 minus 5.495 times 10 to the negative 4. Make sure you're putting this value in parentheses so that you're not just dividing by this and then subtracting this from the entire compound, but all of this needs to stay in the denominator. Oops. Goodness gracious. All right, so we have 0.01945. And all of this then is equal to 1.55 times 10 to the negative 5. Let's make sure you can actually see that. There we go. All right, so again, that's it. Seems complicated because this ice table, might take up a lot of room on the paper or the whiteboard, that kind of thing. But it really isn't if you think about it. We'll do some more problems though, so hopefully it'll get a little bit easier here. All right, calculating Ka from H3O. A 0.2 molarity solution of acetic acid, which is CH3COOH. You'll recognize acetic acid from your acetate compound on the common polyatomic ions. It has a H3O solution or concentration of 1.9 times 10 to the negative 3 at equilibrium. That is key right there. Calculate the Ka of acetic acid. All right then. I'm going to keep the ice table up here. Maybe it will help speed things up. So first thing we want to do is write out our dissociation reaction so we can find out all of the compounds we're looking for. Whoops. Okay, so we have this with our acidic hydrogen plus water, which we're not going to include because we don't need it in our ice table. Essentially just turns into then CH3COO minus plus H3O. So originally it says this is a 0.2 molarity solution, therefore these are zeros. At equilibrium, we have H3O. It's actually telling us, it's not even telling us pH, it's telling us what H3O is at equilibrium, which is 1.9 times 10 to the negative 3, which means your conjugate base has to be the same value. Therefore, the change is here, which means our acetic acid change decreased by that much, that same value. Therefore, we have 0.2 minus 1.9 times 10 to the negative 3. Plug this all in. Here's for your Ka equation, you have these two on top multiplied together, which means we are squaring that value. And then divided by your 0.2 minus 1.9 times 10 to the negative 3. Here's your CH3COO minus times H3O, your products, divided by your reactants. And all of these values are at equilibrium, which is important. All right, so we have 1.9 times 10 to the negative 3 squared divided by 0.2 minus 1.9 times 10 to the negative 3. Make sure you use parentheses again. And we get 1.8 times 10 to the negative 5. There you go. All right, we're going to do some more practice. First, let's look at this equation. This is an equation that's on your periodic table. It's called percent ionization, and it's actually under, at the very bottom of your acid-base box right here, the very last one says percent ionization H3O divided by acid times 100. And that's exactly what we have here. Your we're trying to find the percent of ionization. So how much has the acid ionized? Ionized meaning becoming an ion. And our H3O is the value for that. So you take your H3O concentration, however much it did, or however much it was produced, divided by the original concentration of your acid, and that's what HA is representing. Times 100, of course, that's what we always do for percents, and there you have that. So let's move on. We'll do some practice with that, but for now, let's just keep that concept in mind as we talk about this right here. On your periodic table, we have, it's actually 2 equations above the percent ionization equation, and it says Ka is equal to x squared divided by A minus x. That is your general equation for your Ka. If you notice, that's what this form is in. Your x is representing H3O, which is here at equilibrium. It also even says that there, where x is equal to H3O concentration. Because H3O is always equal to the conjugate base in the equation, you have x squared. H3O times the value again for your conjugate base. And then A is the concentration of the weak acid. So it's the concentration of the weak acid originally that's almost always given in the problem, or you'll have a way to find it from the problem's information, minus x, which is again the value for the H3O. So that is your general equation. Since most weak acids are going to separate or ionize less than 5%, it's a tiny little number, x is so small that when you say A minus x, it's almost always equal to just A by itself, if we're still going to look at your significant figures. For example, let's try that. Take your 0.2 and subtract 1.9 times 10 to the negative 3. So my value, just for this part, just what was in the denominator, says it is 0.1981. Now, if we need to continue rounding this to 2 significant figures, look at 2 significant figures. Look at this 8, that rounds the 9 up, which would then round this up. So we still have 0.20. It's the same thing. X is so tiny, you still have x, or you still have A. Basically what this is saying is that in most problems, you can ignore the x in the denominator. Because think about what if you were trying to solve for x. If you're trying to solve for H3O, so you had x squared up here and an x down here. When you have an x both in the numerator and in the denominator, you would then have to use the quadratic formula. Quick note, I will not require you to use the quadratic formula. Even if you were to take AP, you do not have to use the quadratic formula for these problems. But what you get to do instead is just ignore the x. And we'll do a problem that shows this as an example. And that's because we're not fudging math, we're not cheating math. Basically what that's saying is if you had 1 billion jelly beans and you ate one of them, well, you'll basically still have 1 billion jelly beans, right? It would take you a year to try to count them all again and be pointless because you would basically have 1 billion still. That's what we're doing here. We're just going to ignore the x because it's so tiny, it doesn't actually change the value of it. And it wouldn't change this value either, rounded to 2 significant figures. So let's go ahead and put this into practice so we can actually see what's happening here. So here it says, find the pH of 2.5 molarity solution of HF, hydrofluoric acid, and it's giving us the Ka. So in order to find pH, we need H3O, right? Well, guess what? H3O is what X is equal to in our Ka equation. So that right there is a little bit of a roadmap for how we can start solving this. We're trying to find pH. Write out your equations here really quick, or at least underline them on your periodic table. pH is equal to the negative log of the concentration of H3O. And then H3O is what X is equal to right here. A minus X, we'll ignore the X in a moment. And our Ka is equal to what's given in the problem. So let's go ahead and write that out. We have 7.2 times 10 to the negative 4. Let's make sure we can see this a little better. All right. So if we can solve for x, then we can plug in x for H3O because x is equal to H3O. It told us that the 2.5 molarity is A. 2.5 molarity solution of HF. So that A is equal to the concentration of your acid. Now, X is so small that we can ignore it. Meaning that when we do find X, it is so tiny, we're still going to have 2.5 down here if you were to try to subtract X from 2.5. We still, of course, have to use X in the numerator. So we have 7.2 times 10 to the negative 4. And that is equal to X squared divided by 2.5 because we're plugging in our number, our value for A. Now it's a simple algebra problem. We don't have to worry about that X down there. No quadratic formula needed. So using algebra, we're going to multiply both sides by 2.5. So we have 7.2 times 10 to the negative 4 times 2.5. That is equal to X squared. So if we take the square root of both sides, let's go ahead and actually solve this to kind of get some of our math done here. 7.2 times 10 to the negative 4. So what we have, 7.2 times 10 to the negative 4 times 2.5 is 0.0018. So now let's take the square root of that. And then that means X is equal to 0.0424. All right, well, is that the end of the problem? No, it's not, because it's asking us to find the pH. And this was H3O because X is equal to H3O. So let's go take the negative log of that. Negative log of 0.0424. That is equal to 1.37. Let's look at significant figures. From the original problem, we were given 2 significant figures, therefore we need 2 decimal places in pH. And we've got that. So 1.37 is the answer to this problem. So all of a sudden, these problems are so much easier because you have this simple equation. We don't need to write out your ICE table over and over and over again. We can just use our equation where Ka is equal to x squared over A minus x. We still have that minus x in the denominator written here to remind us that it is there. We just, in every single problem I give you, you're going to get to ignore the x in the denominator. Let's do another example of this. Find the pH of a 0.275 molarity solution of hypochlorous acid solution. Ka is this, 3 times 10 to the negative 8. All right. So again, we're solving for pH. Here's our equation. So if we can find H3O, we would be well on our way to finding the answer. We have our Ka equation as x squared over A minus x. In the problem, we're told that Ka is equal to 3 times 10 to the negative 8. And we're told that A, which is the concentration of the acid, the problem is telling us is 0.275. Let's plug this into here. So Ka is 3 times 10 to the negative 8. X is equal to H3O, and that's what we're trying to solve for. We have A is 0.275 minus X from the problem. Again, okay, well, here's your test. If your Ka has an exponent of 10 to the negative 4 or smaller, so like 10 to the negative 8 is a smaller value than 10 to the negative 4, you get to ignore the x in the equation. So we just ignore it. Again, we're not fudging, we're not cheating math. Don't worry, your math teacher would be okay with this, hopefully. Because x is so small that you're still going to have 0.275. You eat one jelly bean out of a billion, you still have basically a billion jelly beans. It's not going to change your math any. Not going to change the value. So, algebra right here. 3.0 times 10 to the negative 8 times 0.275 is equal to x squared. Let's multiply those. 3 times 10 to the negative 8 times 0.275. So we need to take the square root of both sides. So take the square root of these two multiplied is 8.25. And that is going to be equal to x. So let's do that. And then x is equal to 9.08 times 10 to the negative 5. See how tiny that is? You've got 0.0000908. So if you're to take that and subtract it from 0.275, we've got 4 zeros, in fact, before you can get there. So yes, you still have 0.275. It didn't change the value, which is why we get to delete that x from the denominator. But of course, that's not our answer. That's only H3O. We need to take the negative log of it to find the pH. So negative log of that value. Oops, there we go. All right, 4.04. We have in the problem, we were given 3 significant figures in the concentration, but only 2 significant figures in the Ka. So we want 2 decimals for pH. And we've got that 4.04. All right. Next example. The pH of a 0.1 molarity solution of HN3 is 2.85. What is the Ka of HN3? All right, let's go ahead, back up a little bit here. So it's telling us the pH. So we don't want this equation because we have pH, but we're probably going to need to find H3O. So we say 10 to the negative pH, I don't need the little caret, is equal to H3O. Ka is still equal to this equation. We're not given Ka, we need to solve for Ka. And A in the problem is 0.1, and it tells us pH is 2.85. Which then if we plug in this to up here, we can find our H3O concentration as we have 10 to the negative 2.85. So that means our H3O is 0.00141. All right, and that's x. H3O is x in our Ka value. So let's go ahead and plug that in. We've got 0.00141 squared over A is 0.1. You can see already that our x is small enough that it's not going to change 0.1. Because it's an easy math, you can throw it in there if you want, or you don't have to. We're going to do it both ways to see if it does make a difference or not. So I'm going to rewrite it out again and just write 0.1 underneath. So there's where we are using the x, and here's where we're just erasing the x from there. And we'll try it both ways. Okay, so for the first one up here, we have 2.02 times 10 to the negative 5. Now for this one, without the x in the denominator, we have it rounds to 2.00 times 10 to the negative 5. Tiny difference. With sig figs, actually we only need one significant figure though. Look at that. Our concentration. To sig figs, it's still the same answer. So there it is, both ways. Alrighty. Next one. Aha. So there's only a few more slides actually, because your weak bases are very, very similar to your weak acids. There is a weak base dissociation reaction where you have ammonia, NH3, plus water turns into NH4 and OH, because this time water is acting as the acid and is going to give up a hydrogen to NH3. So the bases react with water, they accept hydrogen from water, thus producing hydroxide. So here's an example of how ammonia, even though we said it can't produce hydroxide and it was our only exception to the rule, In a sense, the solution is still producing hydroxide because ammonia is taking hydrogen from water, leaving hydroxide left. So in essence, it actually does still produce hydroxide, which is kind of interesting there. All right, let's look at our next problem, or our next slide. Here's your general base equation where B minus is representing your bases. Not all bases have negative signs, but this is just showing, look, bases, it's reminding you that bases want to accept a hydrogen. So a base plus water turns into the HB because the base has accepted the hydrogen and water's left as hydroxide. For the generalized weak base reaction, the equilibrium expression then looks like this, where you have KB instead of Ka. It means the exact same thing, it's just for a base, where you have your products, HB times hydroxide, divided by your base concentration. Water is again excluded because it is a liquid and not an aqueous. Here is your list of weak bases. You've got your base formula and name. You've got your Lewis structure for it. You got it with a conjugate acid, or what it looks like as the conjugate acid, which means after it's already accepted the hydrogen, what does that chemical formula look like? Then you have your equilibrium reaction, and you've got a bunch of values for Kb. Again, this one is starting at 1.8 times 10 to the negative 5, and then decreasing in value to 3.3 times 10 to the negative 7. The higher your Kb value, the stronger the base. In the same way that the stronger the Ka, the higher the value it is. Stronger base means it's going to, in a sense, be a greedier compound. It's going to take the hydrogen over a base that is less of a base. It has a weaker Kb. It can't take the hydrogen as quickly or violently. All right. On to practice problems already. So, what is the pH of a 0.15 molarity solution of NH3 of ammonia? So there's your chemical reaction, and your Kb, NH4 times hydroxide divided by NH3, and that is equal to 1.8 times 10 to the negative 5. So they're telling us what the Ka or Kb is, so that's wonderful. It says set up an ice table. I'm pretty sure we don't need to do that because we have our equation, but it's going to look a little bit different for the base. Let's go into the ice table here. In fact, I've got it on the next slide. So we have NH3. We can ignore water for the moment because it's not going to be set up in our equation. And then we have NH4 plus hydroxide. We have 3 rows and 3 columns. I for initial, C for change, E for equilibrium. Now, the problem said that originally the concentration of ammonia was 0.15. So we have 0.15 molarity. Of course, initially, we're going to have zeros for ammonium, the NH4, and hydroxide. What else does the problem give us? I got to go look at that. Oh, it just gives us the Kb. We have 0 and 0. What am I missing? Kb is NH4. Oh, we have the Kb. That's my problem. Okay, oh yeah, this is interesting. Here, well, I'll keep that there. So we have minus x plus x plus x. And x is just because we don't know what the change is. We don't know what our concentrations are. So this is going to be equal to x and x because 0 plus x is equal to x. 0.15 minus x is what your concentration for ammonia is at equilibrium. Because we know what Kb is, we can plug that in, 1.8 times 10 to the negative 5. And then we have NH4 and hydroxide are both equal to x. So let's just plug those in, substitute that in there. So we have x squared. And then we have 0.15 minus x in our denominator from here. So we have equilibrium concentrations for all of our equation, or all of our compounds here. So now we need to solve for x. In this case, x is going to be equal to hydroxide. So once we have hydroxide, though, we could easily find pH. If you were to try to solve this, you would have to use the quadratic formula because your x in the denominator and the x in the numerator messes things up. You can't, it's not simple algebra anymore. Again, I will never ask you to solve one of these equations using a quadratic formula. College Board and on the AP exam won't even do that. So those of you who are looking forward to AP next year, don't worry. Still no quadratic formula. Just so you know, it's easy that way. You get to ignore the x in the denominator if your KB value, same as the KA, has an exponent of -4 or greater, making the whole value smaller. So we do, we've got 10 to the -5 there. So we get to ignore x in the denominator. It is so small, we're still going to have 0.15 as our concentration here. Now it's just simple algebra. So we've got 1.8 times 10 to the -5 times 0.15. We're multiplying both sides by 0.15. That is equal to x squared. Take the square root of both sides. So in here we have 2.7 times 10 to the -6. So then take the square root of that. And that x is then equal to 0.00164. But x is equal to hydroxide. So if we take the negative log of that, we're going to get POH, not pH. But then, of course, we've got a quick fix to translate that into pH. So we have negative log of 0.00164. So our POH then, I'll write out the equation. Oops. So then POH, negative log of this, gets us 2.785. And then pH is equal to 14 minus POH. So 14 minus 2.7 is going to be 11.215. Let's look at significant figures though. Looks like we only need 2 significant figures. So that's only 2 decimals. So we would need to round this to 11.2. Oh, actually, the original problem is 11.21. With the original, I rounded and then rounded again, so don't do that. All right, there you go. There you have it. That should be fairly easy. Let's move on then. All right, so there's your general equation. It's on your periodic table. Kb is equal to x squared divided by b minus x, where x is equal to hydroxide. And again, you can almost always, well, I should say always, ignore the x in the denominator because it is so small, it's not going to change b. All right, let's do this problem. Find the pH of a 3.5 molarity solution of ammonia. So we got the same chemical equation, in fact, we just have a different concentration of it. We're not going to use our ice table because we really don't need it. We're going to make this a lot simpler by just using our general equation. I'll keep our chemical reaction up there. We can add water just because to keep it nice. We are given, so pH is what we're looking for. That's how we can find pH, by using POH. Negative log of hydroxide is POH. Because x in our Kb equation is equal to hydroxide, so we have to use that extra step there. Kb is equal to x squared over b minus x, where x is equal to hydroxide. In the problem, it tells us Kb is equal to 1.8 times 10 to the -5, and it tells us B, the concentration of ammonia, is 3.5. So plugging things into here, we have 1.8 times 10 to the -5 is equal to x squared, that's what we're solving for, we're trying to solve for hydroxide, divided by 3.5 minus x. Because our Kb is 10 to the -4 or greater, or smaller, depending on the way you want to think about it, we get to delete the x in the denominator. Now it's just simple math again. 1.8 times 10 to the negative 5 times 3.5. Ooh, kind of crooked there. Let's go ahead and multiply that out and then take the square root of it. 1.8 times 10 to the negative 5, 3.5. Okay, so we are going to take the square root of 6.3 times 10 to the negative 5, and that is equal to x. Square root of 6.3 times 10 to the negative 5, and that's equal to 0.00794. That is equal to hydroxide. So now if we say POH is equal to the negative log of 0.00794, that's going to get us POH. So POH is equal to 2.100. Of course, it doesn't want POH. The problem is asking for pH. So subtract from 14. And pH then is equal to 11.899. Significant figures, we want two sig figs, which means we need two decimals. So it's 899. That would then have to round up to 11.90. And there's your answer for that problem. All right, we're going to see if this works here. I want to show you a little visualization of acids and bases. As soon as this loads, and then I believe this is our last thing. So let's look at the introduction. This is on your slides, of course. So if you were to open up the slides from Google Classroom, you could find this and then go ahead and play with it. So we're going to put our little pH probe in here. And it says pH is 7 because right now we have just water. Our two water molecules turned into H3O and OH. Now, if we were to put in a strong acid, this is what this would look like. You're going to have a lot more of the H3O, pictured as the little orange molecules, than you do of hydroxide, which is the blue molecule or atom. If you have a weak acid, there's going to be less of it. So it's going to still show a lot of that HA, which is the acid. And you're going to see that some of them turned into, using water, your A- and your H3O, but not all of them. Same with the strong base. You can see they're using M instead of B in this equation. M and hydroxide is your base, and it turns into M cation and M plus and OH minus. So those are pictured with your blue and yellow molecules. Now, if we have a weak base, though, okay, they're using B now as your base and water. And you can see that there's a lot of base left over and only a little bit of them turned into your BH positive and your OH minus. So there's a little bit of a good way to visualize how all of this works, how the complete dissociation is different from the partial dissociation. Then if we were to go to this one over here, we can make up our own. Between acid or base, we can pick our own concentration here. With different ones, you can see how the pictures change in there. You can show the solvent, which then has all of your water molecules, because the water is your solvent, shown in the background. I think that looks a little bit complicated, so I would keep that off. But then you could also look at a graph, find your equilibrium concentration, and we can hide all of it if we wanted to. We can move on from there. So I'm going to see if I can write up a lab simulation for you on this, where you can explore this a little bit better and actually get a better idea of pH, as well as your weak and your strong acids and bases. All right, that should be it. Yes, indeed.